far. Welcome to the Device Control and Integrating this System Session 1. First up, we have the speaker, Amitav Yadav. He is a fellow at the Radiation Protection Group at CERN, and his title of his talk is an autonomous TCP/IP-based multi-architecture C networking library for DAC and control applications. So, Amitav, if you can please share your screen.
Yes, thank you, Johan, for the introduction. And if you can see my screen.
Yes, looks good.
Yes, let me just present. Okay, is it visible now?
Yes, looking good.
Okay, perfect. Thank you everyone for joining me for my talk today on Romulus Lib. I'm presenting on behalf of the Chrome team at the Radiation Protection Group of CERN, and this talk is about Romulus Lib, which is a C networking library that we developed for multi-architecture support in our radiation monitors. So first of all, the agenda of this presentation, I'll start with a brief overview of the Chrome radiation monitors, which is the new generation of radiation monitors at CERN. Then we'll talk a little bit about how it's integrated with the SCADA supervision system and what motivated us to develop this library. And following this, I'll discuss the details of the Romulus protocol and how it's implemented in the library structure and what kind of functionalities are offered through the library, followed by the applications on how it is being used currently at CERN and at the European Spallation Source, ESS. So the CERN radiation monitoring electronics is the abbreviation is CHROME, is the new generation of radiation monitoring systems and alarm and interlock generation systems deployed. So as you can see from the map on the bottom, the first installation has been carried out for the run 3 of the LHC, and in the next step in 2028, the consolidation of the Ramses monitoring electronics will happen for the next run. So there are two methods, there are two architectures in which the Chrome radiation monitors are assembled. The first one is the bulk one, which is for the low and medium level radiation areas, and the rack system, which is connected with an SPA6 cable to the electronics for the high level of radiation areas. And this monitoring electronics has been developed on a Zinc 7000 series SoC, which has a 32-bit ARM processor core and an FPGA fabric, which communicate via a shared VRAM memory space. On the PS, we run a Yocto project built customized Linux, which is responsible for data storage, supervision, management of more than 200 parameters across 8 measurement channels with the CERN SCADA supervision, which is called REMUS. And this communication happens over the TCP/IP network. On the PL side, on the FPGA fabric, all the safety critical applications are running. This includes the measurement algorithms, the dose rate calculations, and interlock generation and alarm generation, and so on. So for the integration of Chrome with the SCADA supervision, we have the Romulus Lib, which sits on the client side of on each devices on the client side, and on the supervision side, it rests on top of a WinCC open architecture API, and all the communication happens over using the TCP/IP protocol on the CERN technical network. For reliability, we wanted to develop a library that can handle this communication with robustness, so that no false parameters or unexpected behavior parameters can be communicated to the devices. So this was one of the motivations early on for the development of the library. Currently, the SCADA supervision REMUS handles more than 2 million measurements per hour using our library with the Chrome devices that are operational at CERN. So at CERN, we use different kinds of control systems, including the PLC to SCADA-based control system, which are widely used in cryogenics control for accelerators, for cooling systems, for HVAC, and so on. And also the SOC to SCADA-based systems are employed in DAQ and control systems in different detectors such as Atlas. And some libraries also exist for this. For example, protocols like Profinet and Ethernet IP already existed, whereas some new libraries started developing. So we started the development of RomList-lib in 2017, and this was also followed by the development of Quasar by Atlas, which is based on the OPC UA. So what RomList-lib does is it offers a full-fledged TCP/IP protocol communication, and it has the functions to construct these frames, validate these frames, and communicate them to the supervision system over the network. And we have made use of the POSIX standard, specifically sockets for support on multiple architectures. And we have tested the library with GCC on x86 architecture and the ARM32 architecture, and also the macOS kernel. So there are four main functionalities of Romulus library. The first one is performing the TCP/IP communication itself. The second is constructing the Romulus frame, the data packets, which I'll talk about in a second. And the third is that it offers multiple modes of communication for streaming data over different channels simultaneously for multiple devices. And there are a number of utility functions, such as reporting of warnings, errors, logs, print functions of custom frames that are designed, and measurement structs that we have defined, and so on, and the checksum functions, of course. So among the modes of communication, the simple mode of communication is one where the supervision sends a request frame and one response frame is sent from the packets. This can be like request of a status of a specific field. And the second mode of communication is complex response scheme, which could be when the first one could be one frame of request is sent from the supervision, and n defined number of frames are responded to by the devices back to the supervision, followed by a frame complete or done response from the devices. And then there's the streaming like scheme, where one request is sent by the supervision, and possibly an infinite number of frames are responded to by the devices, unless either of the sides terminate the stream, or stop command is sent by the supervision. So the data frame is the Ethernet MTU side, which is 1500 bytes for the TCP/IP frame. And apart from the TCP and IP headers, Romulus data frame and ETH checksum, there are also headers for the Romulus data frame itself, which is 23 bytes of header, which contains information about the device ID and the command instruction that is being communicated. And corresponding data is contained for that respective command that has been sent, or in the response it is sent. And the footer is, of course, the checksum footer for error correction. So in Romulus, all the communication happens over measurement channels. So these are the actual spots where the data resides that we want to communicate. So this is defined through C structs. Every measurement channel is defined through C structs, and most common C data types have been employed in the library to support maximum flexibility. And this can be customized. Each measurement channel can be defined and edited to accommodate the DAC and control needs. So currently at Chrome, we are using 8 measurement channels, like real-time stream channel, struct channel, parameters channels, and so on. So this is just briefly an architecture of the Romulus library structure. So there are a number of headers. The Romulus header defines the main initialization functions, timestamp, data structs, and so on. And then you have the Romulus frame, which defines the functions related to the construction of the frame, the validation of the frame, the ID generation. The net handles the networking. The internals manage the internal data structures for printing, checksums, and the HIST is specifically designed for managing the historic data or event management related functions. There's also a leak check function for checking the memory statuses and leaks happening there. And the serialization function happens the data read functions from the specific files. So if you want to build the Romulus lib for the DAC and control applications, there are 3 simple steps. This first is We define the measurement channel. We define this through a gen file, which is nothing but a text file, where we define what parameters that we want to communicate. Then we do the make by specifying the appropriate target. And after doing make, the library generates the necessary executables that you can install in the user library directory. And then we can import this, the specific functions in our embedded application and make use of all the functions that are present. And while developing, there are a number of other applications that we have provided as to facilitate more debugging, like remote stream, which prints the real-time data stream struct info printer, and remote dump for basically querying the devices for necessary information. So currently,
almost out of time.
Okay, just quickly conclude then. So there are 150 devices installed at CERN, and we are using version 6.2, and version 7 has already been released for Romulus Lib. So Romulus Lib is also being used at EPICS, with EPICS at European Spallation Source with the Chrome devices. And yeah, so, and there is a robust testing framework for the Romulus Lib, which is a separate talk that you can listen to on Wednesday. And yeah, with that, I conclude that yeah, the Romulus Lib is meant for networking on the TCP/IP networking, and can be included and integrated successfully with your embedded application and the SCADA supervision. And with that, I thank you for your attention. If you have any questions, please let me know.
A minute or so for questions. Any questions? I see one question from Sebastian. Please give us a question, Sebastian. I think you're muted.
Hi, can you hear me?
Yes.
Yes.
Okay, sorry, I was having a short problem with the microphone. Yeah, so my question is, why did you decide to write a completely new library and develop a new protocol instead of, let's say, just using an OPC UA stack or something similar?
Yeah, so this decision was mainly a design choice made back in 2015. So back then we were looking for libraries that can integrate with SOC embedded systems, and we found that there were some libraries for PLC to SCADA, but there weren't a lot at that time that integrate seamlessly with the SOCs. So we decided like it would be better to have a very like an integrated close to the system library that can function with our firmware. So that was one of the reasons when we started. Does that answer your question?
Yeah, I think it does. Thank you.
Okay, thank you.
Thank you for that question. Mike, over to you.
Okay, thank you. And next we have Ulrich Schwanke. Ulrich is a staff scientist at Humboldt University in Berlin, and he'll be speaking about control, readout, and monitoring of the medium-sized telescopes and the Cherenkov telescope array.
Okay, I hope you can hear me all right.
Yes.
And you're seeing my slides?
Yes.
Can you see them?
Yes.
Excellent, good. Okay, yeah, I will be talking about a topic that is connected to the Cherenkov telescope array, which is a future installation of imaging atmospheric Cherenkov telescopes. And here the image is an artist's impression how the system might look like in a few years from now. And what you're seeing is that we have different types of telescopes. They are called large-sized telescopes, right here in green, the medium-sized telescopes, and the small-sized telescopes. This is because we have different requirements for detectability of gamma ray showers at different energies, high and low. And the table is showing you the numbers of telescopes that will be there in the so-called initial alpha configuration. Yeah, so in the CTA north side on La Palma, there will be 13 telescopes, and in the south near Paranal in Chile, there will be 51. And on top of that, there will be atmosphere monitoring devices like LiDARs and atmospheric like weather stations. And the control of all these devices is the task of the array control and data acquisition system. So that's the hardware that is used to control all the telescopes, to read and store the data. And that's quite a complex system because it has to deal with the fact that we want to observe different sources with different groups of telescopes. And also it's possible that scheduled observations will be interrupted by external triggers or internal triggers. But certainly this challenge that there are different telescope types and different atmospheric monitoring devices is also quite a big one. Fortunately, in the project quite early, we developed a software architecture for ICALEPCS. This was done using the unified modeling language and the systems modeling formalisms. And I think this has been presented at this conferences. And basically on the left-hand side, you're seeing a plot with the basic building blocks in the software. And all this is implemented using the ACS framework, so the ALMA Common Software and the OPC as the protocol of choice for communication with hardware devices. Of course, OPC is not the best thing for a very high bandwidth application. So for our most important task, namely the storage of the bulk data from the Cherenkov cameras, we're also using dedicated solutions. In this talk, I want to focus on one aspect here, which is circled with this, this green ellipse, namely the interface between ICALEPCS and the telescopes. And as somebody working on this medium-sized telescopes, I will show its implementation for the MSTs. The basic design principle was that any telescope can be controlled by ICALEPCS without knowing its exact type. So obviously any LST, MST, or SST should look like ICALEPCS, like any other telescope. And this telescope is part of the software architecture. And basically it's prescribing the usage of a finite state machine, a set of high-level routines, and the number of functions that are returning basic housekeeping information about every telescope. So this housekeeping information is, for example, the telescope state, but also the current pointing direction of the telescope. The plot is showing you basically the state machine or the states that exist for a telescope. We have 3 hardware states: off, maintenance, and on. And then this hardware state on, that's basically a software state, and that's where all the interesting stuff is taking place. So the observations and the calibration and so on. So basically we have 5 different states: initializing, initialize, standby, ready, observing, that correspond to the different phases in case a telescope is observing a source. And we also have a technical state, which I will explain later, and a fault state that is assumed when something goes wrong. On the right-hand side, you're seeing a table with a number of functions. These are not by far not all the functions that we have, but that give you an idea of the scope of these high-level routines. So we have routines that allow or that correspond to the allowed transitions between the states. And we have high-level routines that are almost like physics, so where you tell a telescope to go to a sky target and to observe it until ICALEPCS is changing its mind, or to go to a proper motion target, say in case it's a planet, or to go to a fixed position in case you want to point the telescope to a fixed position in the sky to do some calibration, say. All this interface is defined and documented at the ACS level. And that implies that it's also using ACS mechanisms. So for example, callbacks for asynchronous calls to implement all this. It's quite a high-level interface, and detailed hardware control is also not intended here, but I will show you in a minute that it is possible at a lower level. Here on the left-hand side, you're seeing the software architect view of this interface. So basically here up we have ICALEPCS. And then there's a so-called telescope manager that is implementing this higher level interface. So that means that for standard observations, Arcada deals only with a single core object, this telescope manager, that is representing the entire functionality of the telescope that Arcada needs. Of course, there are always special purposes. So if you want to do something more special like calibration or commissioning, then you have to look really at the camera and at the other parts of the telescope. And that's why we also have extended interfaces for the camera and the so-called telescope structure. Yeah, the telescope structure is basically everything that is not the Cherenkov of camera, so the mirror and all that. And it's also true that the state of the telescope is represented by this telescope manager, and it's calculated from the states of the camera and the telescope structure. Here on the right-hand side, you're seeing the states of the telescope structure, and basically you're seeing the same states that we had for the telescope before, but now they are more detailed and more refined. So for example, here in this ready state, you could have substates where the telescope is slewing to a target before the actual data acquisition is starting. So how is all this implemented for these medium-sized telescopes? These medium-sized telescopes, I'm sorry, have a mirror diameter of 12 meters. The image in the center shows you a prototype that was used in this period at the Adlershof campus in Berlin. And it has a focal length of 12 meters. And here in the focal plane, which is flat, you have a Cherenkov camera. And we have actually two Cherenkov camera projects. They're called FlashCam and NectarCam, and they differ in the number of readout channels and also the used hardware and software. Yeah. And then in the center, we have a pointing camera and also a drive and mounts for telescope movement. And then all the mirror is made up of 86 hexagonal mirror facets, and they are fixed at 3 points, and 2 of them can be moved in and out by so-called actuators. These are stepper motors. And with this AMC system, automatic mirror control, we can adjust these mirror facets such that in the end, you're getting one big spherical mirror with a radius of curvature of 19.2 meters. So at the telescope, we also have control systems. And basically, this chart is showing you the connection between the actual telescope hardware at the bottom and the control at the telescope. So let me highlight a few things. We have a pointing camera. It's an OPC server running on a mini PC connected to an optical camera. There's some calibration device. We also have a conditions monitoring system. You can ask me about it if you're interested. And we have this AMC system. Basically, it's a device server where we go in with Ethernet, and then we have an 8-bit microcontroller that is talked to by the help of a custom protocol, and then we talk to the actuators. There are 2 actuators per mirror. Then we have the drive system. It's a drive PLC that runs an OPC server, and then we are using the feedback from measurements to control the drive engines. There's also a safety PLC. This is a very important device that also runs an OPC server, and it's reading out some interlocks and other sensors that are to prevent, that are to implement safety at the telescope. So if the interlock is open, then you cannot move the telescopes and features like this. Yeah, how is MST control now implemented? This is shown here in the lower part. Again, you're seeing the control systems at the telescope. And basically, the telescope is connected by Ethernet to the computer center. And we have 2 types of nodes that are controlling the telescope. For once, we have a so-called camera server. This is receiving the data from the Cherenkov camera and is storing it for about 1 second. And this gives us enough time to check with a so-called software array trigger whether the event has been seen by a second telescope in the array. And if this is the case, then these data are stored. On the other hand, we have this telescope control system that is executed on a couple of computing nodes, and that's the primary partner for Arcada. So this telescope control system gets instructions by Arcada and then forwards them to the Cherenkov camera and to the subsystems of the telescope structure. The telescope control system as such is implemented as a flat hierarchy of ACS components. Yeah, and basically it's implementing the telescope manager and then dedicated CORBA objects for the telescope camera and the telescope structure. For the MST, we are usually or mostly using Java. Also, we're using Python for mocking up, and the camera projects are using C++. But I would say that 90% of the code is written in Java. These Java ACS components are co-located with Arcada in the Array Computer Center. There are some simplifications here. So for example, unlike in Arcada, we are not performing a supervision of components. Of course, at some point you have to call a spade a spade. So when you have implemented the telescope manager and the structure manager, here all these green boxes are ACS components, then you really have to look at the hardware. So here at this level, we have ACS components that really control our hardware. And since this is specific to the MST telescope, we have decided to use an extended interface for the telescope structure. So this part here, that is specific for the structure, for the MST specific hardware. So if you have a pointing camera, then it will show up in this part. It's invisible to Arcada, but later on MST personnel can use it to say commission or calibrate the telescope. Another feature is that we are using so-called OPCUA to ACS bridges, which you can see here in this box. And basically these are mapping ACS variables properties to OPCUA nodes. So when in one of these components here, you're writing into a local or something that looks like a local, say Java variable, then in fact, you're doing a communication using the OPCUA protocol, and you arrive at the telescope hardware. Yeah, I think this telescope or this telescope control system, all the business logic is in this layer. And the nice thing about it is that all these telescope components here in the green ellipse, they are defining a clear entry point, not only for Arcada, but also for us telescope people. So we, for example, we have browser-based GUIs or expert scripts that are also accessing these entities here and can work with them without knowing how many ACS components we have behind them. And that means that these managers, they're basically are concerned with the state calculation and the delegation of work.
2 minutes left. 2 minutes
okay,
left.
And that's perfect. Yeah. All the business logics here is implemented in few ACS components. And I want to illustrate this with one example, namely the drive system. Basically, we have made a decision that was motivated by safety and maintenance aspects, that everything which is astronomy is happening here in this rather high level code. Yeah, so that means that the PLC at the drive system at the telescope is dealing only with azimuth and elevation. So here at this higher level, we are dealing with astronomical coordinate transformation. We are applying pointing models, and we're generating so-called track tables. These are basically timestamps and then azimuth and elevation. And these are sent to the PLC. The PLC will extrapolate them and then control the telescope. And that's very flexible because you cannot only do sidereal tracking, but you could do something like, I don't know, say sketch a sky, sketch a heart in the sky, or what you want to do. Only higher level safety, so for example, like sun avoidance, is really done here at this high level control. Yeah, that's already taking me to my summary. I think in CTA, we are using a rather high level interface between Arcada and the telescopes. And this has basically settled a lot of discussions about the division of labor between all involved parties. Yeah, this ACS this interface is based on ACS. That's prescribing a finite state machine, and all that needs to be implemented by the different telescope projects. But it's also true that telescope teams have quite some freedom in the implementation. In particular, they can place most of the business logics in the OPCUA layer. Some do that. For MST, we have decided to place all this in the ACS layer because this ACS software, or the software written in ACS, will anyway be maintained for Arcada. Yeah. And then we also have this extended interface. And yeah, I want to finish on the note that firstly, the first real telescopes will become available in a few years from now, and then we will see how the software that we are developing now is doing. And I've deliberately skipped over aspects of monitoring. They will be covered in a talk by Alessandro Costa et al. Thank you very much.
Thank you, Ulrich. There's one question in the QA, so but we are really out of time, so maybe you could just answer it online, please.
Yeah, I can do that. Thank you.
Thank you. Back to you, Johan.
Thank you for that talk. Next up, we've got Augusto Corito, who's a technical development specialist at the Brazilian Synchrotron Light Laboratory. And the title of the talk is Hexapod Control Systems Development Towards Arbitrary Trajectory Scans at Sirius INLS. If you could perhaps share your screen. There we go. Looks good. Yeah, go for it. I think you're still muted, so please go for it. You're still muted, Augusto? Augusto, you're still muted.
Okay, hello, can you hear me?
Yes.
Yes, fine, thank you.
Yes, go ahead. Mm-hmm.
Yeah, sorry for that. So, hello everyone, welcome, and thanks for attending this meeting. My name is Augusto Corito, I'm from Sirius, and I'm going to present our work, which is named Hexapod Control System Development Towards Arbitrary Trajectory Scans at Sirius MNLS. So here's the outline of this presentation. I'm going to start with some introduction. I'm going to explain the motion control development and the validation test we performed. And finally, I'm going to go through some conclusion. So what we had beforehand was that we acquired a BESTEC P478 mirror unit for our motion system in a toroidal mirror in the IP beamline in Sirius. Also, we acquired the BESTEC 494 control system, which has embedded into it a Linux Mint distribution with some proprietary software with some limited configuration parameters. So our main objective was to develop a control solution in-house using our standard controller, the Delta Tau power brick. To do that, we went through some modeling of the hexapod kinematics, and we also implemented it into our control system. To validate our system, we then went through some validation of comparing with the BESTEC benchmark which we had in hand. We also went through some validation of the arbitrary trajectory functionality. So for the motion control development, the first step was to analyze the kinematics of the geometric model based on the draws of manuals supplied by the BESTEC supplier. Here is the hexapod we have. It's fixed, it has fixed length struts, which are moved by vertical actuators. That architecture is due to the fact that the actuators are placed outside the vacuum chamber, while this structure is placed inside the vacuum chamber. Our model was based on the Sirius beamline coordinate system, which is shown in this figure, which differs from the BESTEC one. We chose to modify it to follow the Sirius beamlines standards. For this modeling, we had to define two auxiliary frames, which are shown in this figure. One is shown in the center of the platform, and the other one in the center of the granite base. We also defined a set of vectors for this model, being del, the fixed length struts. The CI is the position of the actuators, and the SI is imaginary variable length strut. The P is the difference between the frames, and then represents the position of the mirror. In addition to that, we had also to define the rotation matrices, which are shown in this slide. So the kinematics is split into two algorithms: the inverse kinematics and the forward kinematics. By the inverse, you have the position of your system, and you calculate the actuators' positions. And the forward is the opposite way. For the inverse kinematics, as our system is a parallel kinematics machine, we could calculate based on analytical analysis only. Starting with the calculation of SI, as shown in equation 1. Having the values after calculating it, we could replace in equation 2 and get the positions of the actuators YCI. We call it YCI as the actuators just varies the Y position. Based on the inverse kinematics equations, we can go to the forward kinematics. For the parallel kinematics machines, the forward kinematics involves nonlinear functions shown in equation 3, being I from 1 to 6 for each actuator. We had to use a numerical method to solve it, so we chose to use the Newton-Raphson method, as it has a fast convergency rate and it's widely used. So we had to define an error function based on the position of the actuators in the Jacobian matrix. Also, we defined a stop condition, which was the error function being less than a predefined error, or we would iterate at maximum 10 times. We watched this system converge at the first or second iteration, tops third one. Having our model, we had to validate it. So we used the Jupyter notebook to simulate a random system position, and we inputted it into the equations of inverse kinematics. We got some position of the actuators, and we inputted into the forward kinematics to have a simulated position of the system. And we compare with the starting position to check if it was the same. After the validation, we used again the Jupyter notebook to generate C codes of the equations and also from the Jacobian error function, which we were able then to import to the controller IDE. We had also to configure some controller scripts like the motion scripts and the configure scripts, and we were able to compile and download into the Delta Tau Power BIC LV. After that, we were ready for operation. The next step was then to validate our control system. We set up the control system we had in hand with the same parameters, like speed. We then had to connect each one of them at a time with our motion system. And we move 1 degree of freedom at a time, logging the position data from all the DOFs. After that, we had to process the logged data to compare the equivalent movements, as the coordinate systems were different from using each control system. For compiling purposes, we had to show only 2 movements. So we chose to show a translation movement and a rotation movement. For the translation movement, we chose the Z movement going from -1 millimeter to 1 millimeter. Here in the plots, you can see that the straight lines represents the BESTEC controller, while the dotted lines represents the developed control system 1. In the Z movement, we can see that the BESTEC control system reached the destination before, but it presents some small position deviations at the transient state, while the Delta Tau 1 represents a smooth movement until the end with less control errors. When watching the other degree of freedoms, we can see that BESTEC controller shows more crosstalks in all of them. And some of them represent an order of magnitude difference, like the rotation in X and Y axis. For the rotation movement, we chose the rotation in X, in Z movement, going from -3 milliradians to 3 milliradians, where the behavior watched was quite the same. The BESTEC controller reached the destination before, but again, with some small deviations at the transient state. In the power brick, again, with less control errors. And also, when we watch all the other DOFs, the Delta Tau presents less control errors, less crosstalks. And one more time, like X and Z, crosstalks represent one order of magnitude. This validation test showed us that the Delta Tau Power BIC LV was validated as the commanded movement presents less control errors, and the crosstalks also were smaller than the previous control system. So our next step was to validate the arbitrary trajectory functionality which consists on commanding the control system with predefined positions and speed or time lapses of the trajectory. Our choice was to generate a trajectory using the Python script. And we used an MOBR algorithm which was implemented by DLS to download it to our control system. The generated trajectory can be seen in this figure. And we decided to generate one where each one of the edges of this square varies 1 degree of freedom, as the plotted shows. The position, speed, and acceleration vary. That's because we would like to show that it's totally arbitrary trajectory. So we generated and we downloaded it into the control system. And this is the logged data against the time. You can see that at each edge, there is 1 degree of freedom that varies linearly, and the other one varies according to the previous plots. We can see that the error ranges from -3 to 3 microns, which is quite enough to control our system. And we validated the arbitrary trajectory functionality. So concluding this work, we developed in-house the motion control system based on Delta Tau Power Brick LV for the mirror unit P468 from Bestech. Their previous controller reached the specification at the steady state, so it's feasible to use it for step scans or steady tests for the beam lines. But the crosstalks during the transient states in movements are quite notable, which makes it not feasible for fly scans, for instance. The design system's accuracy at the transient state overcomes the P494 from Bestech. So we validated that our system can be feasible to use on a fly scan. Besides that, we also validated the arbitrary trajectory functionality, which represents one step towards the system coordinated motion, the beam line. The knowledge acquired in this work can be applied to other systems in the series. The kinematics in C language, for instance, could be applied for granite bases, as it's shown in a poster section by George Contogeorgios. You're invited to come. Also, the arbitrary trajectory can be applied for monochromators in series in the near future. I would like to thank you, the Brazilian Ministry of Science, Technology and Innovation, and also the Brazilian Synchrotron Light Laboratory team. Also, I would like to thank you, Omron Delta Tau, for technical support, and Diamond Light Source for their open source development they've been put available in GitHub. Thanks, everyone, and I'm available for questions.
Thank you, Augusto. I think we've got time for one quick question. Nader?
Yes, thank you very much for your talk. I was just wondering, how did you compare the tuning of the two controllers after all? So how do you make sure that the Bestech is at its best tuning and Delta Tau is at its best tuning?
Yeah, I had to log the data. The only choice I had was to log the data from the system when moving with each one of the controllers. Beforehand, I had some configuration I had to change with the support of Bestech team. And I'm quite sure that they were more focused on the positioning of the system and not the movement, actually. So maybe with some tuning of the movement, logical algorithm, they could be better. But the point here is that for that, we would have to ask them to develop that functionalities. And with our controller, we have the autonomy to implement this functionality and the other ones in the future. Like said here, the arbitrary trajectory. So we tuned that previously with the support of Bestech team, and we performed this comparison.
Thank you.
Thank you,
I hope
Augusto.
I have answered your question.
Yes, please. Yes, thank you.
Thank you, Augusto. Over to you, Mike.
Okay. Next, we have Yuri Krasny. He is a group leader at CozyLab, and his talk on generic data acquisition control system stack on MTCA platform. Go ahead.
Perfect. Can you hear me?
Yes, we hear you.
Perfect.
And we see your slides. Yeah.
Great. Hi, my name is Yuri Krasny. As was already mentioned, I'm a technical lead with CozyLab, focusing on EPEX control systems and micro-TCA hardware platform. I will present a project that we implemented at CozyLab, the generic data acquisition control system. But first, a little bit about CozyLab. CozyLab is a world leader in control system development for big physics and for photon therapy. We were founded in 2004, and we have grown to 10 locations around the world and more than 200 people, from which there are 3/4 engineers. And we've been growing steadily to 20% since our inception. We're a system engineering company and help our customers implement state-of-the-art software and hardware. We provide solutions for particle accelerators on the scientific market as well as medical markets, and also offer multiple products for proton therapy. And we have been growing considerably on the medical market as well, where previously we've been focused more on physics. Some of you already know us and might be our customers. Some of you will hopefully know us in the future. Through the years, we have developed multiple DAQ applications for different particle accelerator use cases. And when looking at the use cases like beam profile monitors, beam loss monitors, and low-level RF, we've identified overlap and shared functionality between all these applications. There's usually, to some degree, also customization on the FPGA layer. So during this gave us an idea, and we posed ourselves a question: can we make a generic control system stack that would cover this core functionality, but also allow users to add customizations for specific use cases? Our goals were, of course, to improve code reusability and reduce code needed to support new devices without sacrificing the ability to extend the functionality for custom use cases. We wanted to cover as many control system frameworks as possible and make the system agnostic to control system frameworks. By having core components, we wanted to reduce expertise needed to support different use cases and create a central standardized code base that all engineers could reuse and learn from. And then finally, we also wanted our code to be portable to different hardware boards with minimal changes. When selecting hardware, the choice was straightforward. We are long users of micro-TCA.4 and have been using it since 2013. We also use it for our internal product, which is a dose delivery system for medical particle accelerators for cancer treatment. The main reasoning behind micro-TCA.4 is, of course, its abundant support from vendors like Valatech and Struk, and a large selection of existing boards on the market. Of course, performance is a big reason as well, and support for advanced features like remote crate management through IPMI. In order to test the system, we use boards from Valatech. You can see them on the slide. The AMC 523. So this is the front end, and through the back end connector, there is a rear transition module, the so-called rear transition module that connects to it. And then this is the mezzanine that goes into the rear transition module. And all the ADCs are on the rear transmission modules, and then all the FPGA is located on the board, and the communication goes through the big connector located here. This, of course, gives you the option as well to develop your custom backend, while the carrier, the rear transition module, and the front end are the same. So you can buy these two components off the shelf and develop your own ADC for your specific use case. The architecture or the application that we call GDAC has a pretty straightforward architecture. The prototype was developed using APEX. So we wrote our custom firmware, of course, and a custom Linux driver. And using rich user space library, we've integrated this into the APEX stack. We're using the NDS driver, which I'm going to talk more about later. And async, of course, the GUIs are done with Control System Studio Phoebus. More about each component later. So one of the main aspects that helped us was, of course, the configuration. We've tried to generalize the code. So we moved any specific data of the hardware into JSON. And this configuration, configuration is stored into a JSON file, which is used by all components in the stack to adapt to a specific board. And also, we also configure the firmware. So a part of configuration is taken from the JSON file and pushed down into the firmware through the user space library. So about the firmware, firmware is generic and has a configurable data width of samples up to 32 bits. The amount of input and output channels is also configurable, and it's capped at 32 channels for each the inputs and outputs. Each channel has a configurable internal buffer, which allows us to optimize RAM usage on the card. Both enabling and disabling the acquisition is implemented per channel, so they're completely independent. We support multiple trigger sources, external, internal, and other. For data generation, we also we can use output channels. We can stream data from RAM, from internal data streams like NCOs or numerically controlled oscillators, or we can read data from input channels, process them, and then output them on the outputs. So in terms of the kernel, the driver was implemented to include as little functionality as possible in order to reduce the amount of code running in the kernel, and therefore also reducing the likelihood of causing a kernel crash due to bugs or errors. The user space library has a generalized C++ API and allows other control system frameworks to be integrated in as well. But it still has a rich, pretty much business logic filled up API. So it's not just a bare bones interface. We've also written the user space library to allow extensibility by exposing the internal register map of the card to user space applications. This allows, this simplifies adding new code and extending the application. So in terms of the APEX support, we used NDS. NDS is, or nominal device support, is a library, an open source library that we developed at Cozy Lab to simplify integration of hardware into control systems. NDS was used, of course, because it uses a general abstraction of the device, and it generates 3 structures of device channel groups and channels. And of course supports both APEX and Tango. Since NDS generates the EPIC database and the Tango device server from code, this was instrumental to allow us to use the JSON configuration that I mentioned before to actually generate the control system databases and logic for EPICs and Tango. If you're interested in using NDS, you can find it on the link that I provided on the slide. The GUI is implemented with Control System Studio, as I already said. We use the newest version that is referred to as Phoebus. Here we can see the analog input channel configuration screen. The channel can be separately enabled and armed. All the parameters of the channel, like clear soft signal mode, can be set here. Once we arm the channel, some of the fields disable, and we get the data. Since all this big data is disabled because they cannot be modified during acquisition. So the data is received based on how the triggering is configured. For output channels, the configuration is similar, and it also includes streaming sources. So You can set the source where the data is streamed from. Another functionality of the output channels is the load data functionality, which forces data to be loaded onboard to the RAM. So you have a specific waveform exposed that's where you can load custom data, and you can force to load it on the RAM here. This also forces or prevents clients being able to overwrite data during playback. When loading data from RAM, we also have functionality that allows partial data to be played. You can see the limitations on the playback with these vertical lines. The GUIs are also generated using JSON. So this list of channels is populated by parsing the JSON configuration and instantiating the widgets dynamically. And there's also a separate, like, bigger channel display screen. In conclusion, I would like to say that the project is still in prototype phase, by which I mean that it wasn't yet used in a production environment. Nevertheless, it works as expected during testing. We have the option to add MRF support to the board, but currently there is still no use case where we would want the board to be an MRF receiver and not have a separate MRF board. Some port for continuous acquisition is more of a niche functionality, so it's not something that we plan to add immediately, but is something that we have on our future list. And that would be all from me.
Okay, yeah, thank you very much, Yuri. It's a good presentation and perfect on time. So we do have time for question. And so I don't see anything in the chat yet. So if anyone has a question. Well, I could ask a question. For this library and for this framework, what scale of the application are you targeting? Are there small kind of tabletop systems or larger facilities? What do you see any limits, upper or lower limits on the size of the systems?
So in terms of the actual performance, I don't think there are limits. I think it could be used on a large scale as well. I would say that in terms of implementing this as your own solution, I would say that the limit is actually the requirement to modify FPGA. Right? So if you want an application, you don't need to modify the FPGA, then this stack is probably, you can probably get a vendor support for one of your boards from the vendor, and if there's no need to modify the FPGA, then this stack is probably an overkill. But if you would throw away the vendor provided code and start developing from scratch, then this would be a quicker approach to get to a prototyping phase where you can, deploy this on your systems and start applying your custom FPGA code to do signal processing that you cannot do fast enough on the software side, let's say. So more of a really high-end use case where custom signal processing is needed. Additionally, if you have multiple hardware boards from different hardware vendors, this stack would also then generalize the interface through all of them, since it can be ported to different boards.
Okay. You also got one more question in the panel Q&A, so please take a look and we'll move to the next speaker. So thank you, and back to you, Johan.
Thank you. And the last speaker for this session is Nader Afshar. He's a senior controls engineer at the Australian Synchrotron, and the title of the talk is Motion Software Developments for PowerP MAC in the Australian Synchrotron. And if you just share your screen, Nader. And you are still muted. There we go. You can see your PowerPoint.
We see your slides. Yep, very good.
Okay. Thank you very much. Hello, everyone. I'm presenting this on behalf of control systems team in the Australian Synchrotron, along with my colleague Ben Baldwinson, which will run over the last part of the presentation. So this is about the focus of this talk is the motion software stack that we have developed for Power Max. We will have a look at requirements, challenges, and limitations, of course, in hindsight, and two specific implementations that we actually concluded to do at the end of some iterations and based on those requirements and challenges. So the motion controller itself, I think it's a familiar Delta Tau PowerBrick LV, now is labeled as Omron controller and repackaged by Faraday into 19-inch racks. And on that one, there has been a lot of different talks. And the one liner that I can add here is that the challenge is to how to utilize the configurability and the advanced features, but keep it maintainable. And that is the secret that we think helps a lot with this controller. So a deep dive into the problem space. I would say these are some of the questions that came up and we had to answer them. Do we still need a motor abstraction layer? And by that, I mean, because we had a new program and we were building new beam lines, there was this opportunity to just have a fresh look at everything and think from a kind of step back and see and question everything basically in the problem space. So one of those basic questions is do we still need a motor abstraction layer or EPICS motor record? And all in all, the answer was yes. We need one. And the other question was the things we do or don't like about EPICS as a whole. Channel access, I would say we like it. It works fine and it solves many problems and it provides the network layer that is essential for controls. But control logic programming in EPICS and everything else doesn't have that much attraction for the control systems. Now, what's the minimum level of backward compatibility to maintain? That's another question. In the hindsight, we know better about the answer to that question. And the other one, for instance, is do we treat controller as part of assembly or as part of the infrastructure? So do we go inside the controller and customize with jumpers and dip switches for that particular application or assembly, or no? We just say, so we concluded that no hardware customization, hardwares will be part of the infrastructure. So this is a block diagram, as I understand, from all of the main systems that we do, and the two main interfaces. The most important one is what we call EPICS interface, or the controls standard interface with PVs, and the one down there from controller interface, which is in this case it's an Ethernet interface, SSH interface, and everything in between and a little bit under that controls interface is what we call as motion software stack, and it happens to be control systems domain of work as well, because we don't have any separate electronics group in Australian Synctron. So control systems people maintain the whole stack of everything under EPICS layer. So one thing that came out of our requirements was that we needed the motor record to support floating point system, as in the readbacks no more in integers, but they can be floating points, because interactions specifically because in interactions with motor and coordinate systems makes more sense and makes things much easier if we are not bound by step or encoder counts. So this is how the motor record traditionally does the scaling. It has these, the urev equals mres multiplied by srev. Srev is step per revolution, mres is motor resolution traditionally, and urev is units, engineering units per revolution. And the following, everything else follows from that basic arrangement. And after some iterations, we realized that the steps there is what's embedded in there as an integer, and that the assumption of readback being always in integer steps is there. So we just changed everything that was in its steps to motor units, which is now a float. And this intuitive change is both necessary and sufficient to make the motor record work in this general case. So now steps and counts are abstracted at the controller level by choice. That means at the controller level, we are free to choose any units for motor units, being revolutions of the motor, for instance, or millimeters or degrees, or if someone chooses, they can still work on motor steps, which are 200 per revolution, for instance. And what's left in the motor record is a scaling between motor units to EGUs instead of between steps and EGUs. And that can usually be 1.0 or something that just represents what's the difference between the EGU at the motor record and the controller. So part of the change is that we realized that MRES had two roles fused in one. One of them is scaling between steps and EGUs. Sorry, I went back and forward. Sorry for that. I knocked my mouse. So the second rule has been the motor resolution as in the minimum incremental motion. So we changed that to that and added axis minimum incremental motion, which is now a separate PV and is more realistic for modern setups. And you can set that up as real as it can be. And it determines the actual minimum motion that you can take. So all in all, we took the DLS based software stack for PowerPmax, and we just worked based on that and improved it in some ways. We fixed and improved in some ways, and also added a new motor record with motor float 64, which has floating point readback, and did some adaptations and streamlining of DLS templates, and also developed a motion test validation software based on Python, scripting the tests and test cases, and it just automates all the test cases. And we're back to the same block diagram, and as you can see, what I was talking about is mostly on the left column, the software stack based on the traditional motor record, and on the right you can see what we have envisaged as a streamlined motor record like implementation using Python, which my colleague Ben will go through that part of the presentation.
Sure, thanks, Nada. Yeah, just talk about today
something we call CAPIMAC, which is kind of fun to say. It's a Python implementation of an IOC for a Power PMAC. Based on Caproto, you may or may not know about Caproto, but it's a pure Python implementation of channel access for epics. And the CAPIMAC IOC is configurable with a YAML file. So why would you want to do this? Why not just use the standard epic stack? You know, it's lightweight, very easy to kind of work with and prototype with being Python. And yeah, for people who are more familiar with Python, then it's just easier. So next slide, please. So we created this kind of glue layer based on async in Python. So it provides calls to the GPASCII program running in the Power PMAC. And that allows us to pipe those commands from the CAPIMAC IOC quite easily. And you can still use that CAPIMAC with any of your standard motor record GUIs. Yeah, again, if you haven't heard of Caproto, maybe this is a bit of a plug for Caproto as much as anything. Check it out. Very easy to use. Next slide, please, Nada. I feel like this has been a bit of a theme in some of the talks that I've seen in this session. We have a bit of a snippet of my configuration file. So it's all in YAML, and you can select your, typical motor record things. You can see MRES I've chosen to use as one there, meaning we would set up the controller in, say, millimeters. And then in your favorite Python environment, you can just run it with the YAML file as an argument. Next slide, please, Nada. Bit of an explanation of what Caproto looks like. So Caproto provides an endpoint for any of your motor record PVs, but doesn't really do anything with it. So this is an example of just trying to fill in what happens when you set the velocity. It's like the .velo field. So if you can write an async command to send a command to an external device, then you can easily pipe that in with Caproto. Next slide, please, Nada. We didn't put in all the motor record fields for this, so we really wanted to pipe in the sort of operational PVs that people would be using most of the time and leave the configuration in the controller level. So yes, things like soft limits, velocity, offset, and a bit of scaling, so offset and motor res. Next slide, please, Nada. With the testing and debugging using Python, we identified a bit of a bottleneck using GPASCII, and that helped with some of the diamond stack debugging as well. But because of that bottleneck, using Python was just as fast for this IOC. And yeah, again, Caproto, check it out. Does need more sort of contributors, and yeah, get involved. That's it. Thank you.
Thank you. I think we can take a minute or so for just one question. Krista.
Okay.
Krista, your question, please.
Hello, can you guys hear me?
Yes.
Yes. Oh, yeah. Yeah. Thank you for the interesting talk. I was wondering on the CAP-PMAC, when you were communicating with the GP-ASCII, have you noted anything else like loss of communication, random loss of communication, or something similar to that? I'm wondering because at Soleil we're using a similar approach, but using Tango devices, and every once in a while we experience loss of communication, and we're not entirely sure if it comes from the network or our approach of connecting to the system.
This is something that I noticed the other day after running it for a while, but I haven't had time to investigate.
Yeah.
I mean, I know that the Diamond IOC will reconnect if it has any issues communicating. So yeah, I guess I'm suggesting just try reconnecting if it does disconnect.
Yeah, we usually reconnect, but then yeah, our devices become, how to say, red temporarily. It's no big issue, but it's something we have seen every once in a while over the years. So just wondering if it was our network or just the GP-ASCII thing.
Yeah, I haven't debugged it to that level yet, but yeah, maybe check in with us another time and we might have found something.
All right. Okay, thanks.
Okay, thank you. Oh, thank you for all our speakers today. If you still have any questions left, please use the Ruva platform to reach out to the presenters. And I believe next up is the poster session, which you can find in the Ruva site on the left-hand menu under the agenda. There is a posters tab you can go visit. And yeah, thank you for all the talks. And I think this concludes the first session for the device control and integration of those systems. Mike, you want to say anything?
No, thank you everyone. Thank you, Johan. See you tomorrow.
Yeah, thank you everybody.